Well, who would have thought you need an oscilloscope to fully comprehend what's going on inside a coffee machine? I mean, come on. Today it's time to relax and tear something apart, like this old coffee maker. Um, it's kind of the electric percolator type, so I expect it to have some heating element, turning the water in the tank here at the top, yeah, into, oh, that's a surprise. Okay, don't mind that. The water in the tank on the top, into steam, which is then going up and coming out. Yeah, it's an old one. Here, half steam, half water, and goes into the filter. And I don't think we need the filter. Well, let's go to it, huh? Oh yeah, there was already missing a part here, a clear plastic tube connected with the water tank through this hole and containing that contraption which displayed the water level in the tank, yeah, for filling it up. Okay. Yeah, and at the back we have four most, can I zoom? Focus. Most service unfriendly security screws, so I have to look if I find a tool for that or if I take brute force. Just a second. Sorry I didn't film that. I am sorry. But that was, yeah, definitely a job for my new Dremel with a small saw blade. Which didn't came by standard with it, I bought it. And I ended up, yeah, just cutting around the screws. And yeah, by the way, that thing was made in France, so made in Europe. And yeah, it's definitely not Chinese. I mean, this thing is so old, there are no real material markings here on the plastic, but you see, it's very flexible, but it springs back, and yeah, you almost cannot break it, so I think it's kind of polyethylene, PE. Yeah, nevertheless, yeah, and in addition, two snap ends. So 3 security screws, 2 snap ends. They really, really want to keep the lid on things, so to say. And also a triple lip. So an outer lip and inner lip. Yeah. Going, and I put that away, going over this lip here. But now that we're in, let's see. So we have the cable, that's nice, and yeah, it goes here through this duct. So yeah, you can, it went to another duct in the bottom I just threw away. Yeah, here. So yeah, a gorilla could pull on that cable and it wouldn't come loose. Well, there's not much to see in here, huh? Besides the rest of the security screws, but nevertheless, let's try to get that out. Yeah, that security screw is holding in something that looks like a heating element. Our cable is connected with neutral to a board, and the board has a second neutral connection. And okay, the board is just in there, wibbly wobbly. I mean, it's probably, and I'm getting the bottom out a third time, and I'm trying to see what held that board in place. Oh, nothing really. No, nothing really. So we have a board here and we have a switch. Sorry, a switch. And that switch is also held in, not by a snap-in. Oh yeah, it must be some kind of snap-in mechanism, I guess, because well, it's not snapped in from the outside, and this is only a momentary switch. So the electronics might be a little bit more interesting than simply on-off. But how do I get that switch out here? So that was the most evil snap-in, and the snap-in actually, focus on that, was here in between, and that recess, and two little tabs, so it wouldn't be visible from the outside, and that the switch only held basically near the axis of rotation, wouldn't wibble wobble. They have these two arms coming out from the inside, pressed against the case. And you might wonder, why are there neutral and two phases? That's because that switch has an indicator light built in. Yeah, and we have a circuit board with big resistors and a diode. I mean, this is a capacitor, and that white blob here is a relay. A 48-volt relay. What the hell were they thinking? I mean, what did they build inside here? Okay, we'll see in a minute. Yeah, the plot thickens. I got the heating element out, and yeah, with brute force broke that screw off, which was holding it in, using already in the garbage that contraption. Yeah, that was affixed here. And yeah, obviously we have that looks like a thermal fuse of some kind. Oh, can you see that corrosion? Yeah, that's earth. And yeah, that is brittle as hell. brittle as hell and all rusted. You see the isolation is basically peeling off as I... That's not good. That's not good, and the copper inside is already, can you see that? Let me zoom in, extremely. Yeah, the copper is also turning to copper sulfate, getting green. Well, that's not a good failure mode, I guess. But anyway, we have at the top what is just a bimetal thermal switch that will, yeah, switch at some temperature, and I guess this here marked 4905 with tabs is, it has another marking, A125KA. Yeah, I'll look that up in a second. That might be a thermal fuse as yeah, last resort. And the contraption itself has yeah, in two distinctive assemblies the heating element itself, which I might or might not pull out at some point, and simply yeah, where the water flows through. And if you look at the state, I simply could pull it out. You see in down there, you see the connections to the water tank. There is something like a valve down there. Is that a valve? Maybe we can get that out too. But if you look at the state of the plastic tubing, it's no wonder why that thing was leaking at the end. I guess that was some kind of silicone, PVC or rubber once upon a time. Yeah, let's put that to the side and let's see for the moment. Let's see if I can get that valve out there. Yeah, it's grainy, but as far as the check valve goes, that's as good as it gets. You see, it's when the pressure, when there's back pressure, the check valve closes, and yeah, let's see it from the other side. You see it down there, and if the pressure is gone, then it opens up again. Yeah, you can see it's open. Sorry. This is quite dark in here for the camera, and so if it's open, water is flowing down. Down is towards us into the heating element. It's heated up, turned into steam, and that of course causes a lot of pressure. And then the check valve is closed from the pressure, and the steam has only one way to go, and this is up this hole into yeah, going down the filter. And yeah, basically you don't have to turn all the water into steam. It's just a little steam and a lot of water, which is then basically explosively. That's why they make that sound pressed up here. And as soon as it's dry again, the heating element, and you basically only have atmospheric pressure in here, no more steam and water to work against, the valve falls down again, and more water flows into the heating element. And with that I can throw this into the trash bin, finally. So let's see what we got here. Okay, let me take a photo from the board and its backside, and yeah, let's try to trace that out, and then I come back to you. So I got a photo from the board and from the backside. The backside I mirrored, obviously, if you look at the cables. And now we can trace the whole stuff. Yeah, that should be pretty easy. So this is all one big island, and yeah, I'm looking here where this is going to, but this is going to the switch, the whole side. Then we have obviously a trace going 1, 2 to that diode here, and we have that resistor connected to that cable, and that black cable, it is black. Oh, sorry. The black cable goes to the heating element. So this is to heating element. And then the diode is connected with, yeah, I'm looking here. The diode is connected to the capacitor, and that's the positive side of the capacitor, and the negative side of the capacitor traces back to, yeah, and this is all connected here. This is all one big island. The negative side of the capacitor trace back to here, and then we have 1, 2, 3 thingies here. 1, 2, 3, and one is connected. One is connected to the capacitor, the other is connected also to the feed from the heating element, like these resistors. And the third one is connected to the positive of the diode. Okay. Yeah, I mean, that pin here, this is, sorry, this is our diode, and these are the 3 pins on that side under the relay. Yeah, that's the case. And on the other side we have 2 pins, one which is, which we can forget, and the other one is also connected to the switch. Interesting. Yeah, these are all going to the switch and to the brown wire. And that's it. And the brown wire is going that one here, is going through the, let's just draw that in, through a thermal fuse. That's a thermal fuse. Brown wire, thermal fuse 2. Yeah. Phase. That's goes basically to L. And the black one I said goes to the heating element. Was I lying? No, the black one is going to the heating element. So, yeah, black on black, sorry. To the heating element, I do that as a coil, and from the heating element it goes black into the gray wire. First black heating element, gray wire, thermal switch. So this is our thermal switch, normally closed. Okay. Yeah, not really a switch, sorry. I will make a nice drawing in a minute. To our thermal switch, and from our thermal switch it goes to blue, thermal switch, blue to the board again. So that would be this one here. And as I said, this goes via thermal fuse to live, and this goes to mains neutral. And now I just have to decode the switch. These 3 wires, give me a sec. Okay, and I just measured the switch, and the brown and black is momentary closed. Yeah, that's this action. Blue is basically isolated when I measured with the multimeter, so I surmise that it somehow goes to a gas discharge lamp built in here. Yeah, it has that indicator in here, and yeah, if it would be a LED I would get some reading, but I get no reading at all measuring it with low voltages. So yeah, gas discharge lamp, and I haven't decided which side it is connected to, and this is now all very convoluted, and I guess I draw it in the clean. just a second. So I cleared up the whole thing a little bit, and yeah, at first glance it's quite primitive circuit. We have here live coming in with 330 volts effective, or that's 325 volts peak. And we have our normally closed, that's the big thingy here. That's actually a thermal switch. Didn't found any data, but let me focus. Yeah, the marking A125KE. That's basically a good indication that this is a thermal switch that will actually switch at 125 degrees, and consequently the smaller thing at the side is just a thermal fuse. It has no markings, so yeah, I'm going with thermal fuse here. Maybe resettable thermal fuse, and but it has a role of a thermal fuse. So initially nothing happens, because if you live goes through the thermal switch, through the relay, which is normally open, through the heating element, through the thermal fuse and neutral, and since the relay is open, nothing happens. Now, if the momentary switch, that thingy, is closed, the capacitor is charged through that 10K resistor and the diode. And as soon as the voltage here reaches 36 volts, the relay closes. And I could find a data sheet for the relay. So the coil is nominal 48 volts, and it's working in a range from 36 volts. It will start to close to 60 up to 62 volts without cooking, and it has a resistance of 6.4K. So as soon as we have 36 volts or above here, at that point the relay closes, and then of course our circuit is closed and our heating element is heating up and evaporating, turning water into steam, whatever. And at the same time, even if we release now the momentary switch through that 5.6K resistor and the 10K resistor, the capacitor is constantly charged now, and so the relay coil is gets constantly current, and our relay is closed. So machine running until we run out of water. As long as we have some water here and the heating element, the temperature will stay around 100 degrees C. When no water is there anymore, it will continue to heat up, and that's where the thermal switch comes in. The thermal switch at 125 degrees, from the markings, it will open, okay, and it will basically isolate the whole circuit from live. So our resistor is no longer charged, our capacitor is no longer charged, so it will discharge completely through the relay coil. The relay will also open, and everything is off again. As soon as the whole heating element assembly cooled down, our thermal switch will close again, but then the relay is open, and we have to press the momentary switch once again to start the whole process. So that's all fine and dandy, but yeah, if you look just at the resistors here, and yeah, take the relay coil as a 6.4K resistor, we never ever dropping the 325 volts peak to a safe level of 62 or 63 volts. Yeah, let's say best case 15K. Yeah, it doesn't work. The numbers don't work out. You would end just with the resistors here in the range of 100, 200 volts, and that would kill your relay coil and your capacitor. Two things to keep in mind here. First of all, we get here in AC, so full sine wave with peak to peak of roughly 650 volts. The diode basically makes sure inside this circuit we are only using the positive half waves. So we really inside here we really have only to deal with the 325 volts peak. So, but yeah, still. And yeah, we only have half sine waves rectified. And basically without that capacitor, the relay coil would actually be cooked. But yeah, you can look at this as a voltage divider. So the current going through both resistors, or if the switch is closed, only through that one resistor here, there are two currents flowing here. There's one current flowing through the relay coil, and there's a second current flowing through the capacitor. And yeah, you can, if the switch is closed, if it's open, and we're going through that resistor too, and this, yeah, the charging current through the capacitor actually causes an additional voltage drop here over that resistor, and that obviously, because the electrolytic here didn't explode, causes enough additional voltage drop over this resistor or over both resistors, yeah, to keep the voltages here at a safe level. I won't even try to calculate that using reactants and stuff, and yeah. Oh, one little detail I forgot here. Let me take the other color. We have yeah, we have that indicator light, neon light, gas discharge light, and this must be connected, obviously, because yeah, it's inside the switch assembly to that side of the switch. So yeah, that's it. I mean, this is still a little bit of black magic here if you're not into, yeah, really AC stuff. And I'm really tempted, yeah, to put that thing on an oscilloscope just to see what the charge currents, discharge currents here are. And on not the currents is hard to measure with an oscilloscope, but you know, but that's probably an overkill. So yeah, let's leave it at that. Okay. Of course, I couldn't resist. So yeah. Before I go into the details, a word of warning: if you do anything wrong in such a setup, you can kill your device or your oscilloscope. Because oscilloscope ground here is mains earth, okay? And you also noticed on the probes that I actually don't have the earth clips connected anywhere. They're not even attached. That's because I'm referencing everything at earth ground. And you can see that, but in my lab, all outlets are marked which is the neutral side and which is the live side. And I measured that out and made sure that I plug that one in correctly. So that neutral blue, which we are referencing here, indirectly through the oscilloscope, is actually connected to mains neutral, which should be connected to main earth. And I pre-measured that with a multimeter 3 times in advance, because if you get it wrong, it makes a big bang. I did that once when I was around 15 with a very, very expensive oscilloscope measuring around in a TV set. It was an analog storage oscilloscope, no electronic storage. No, the storage was in the special phosphorus stuff and some additional electrode layers in the CRT tube. And yeah, it made a big bang, and that thing cost back then 10 or 20K. I have no idea. I lent it from an engineer to repair my TV, and yeah, it made a big bang and a big mess. The TV was gone, the oscilloscope lived. I think it was a Harmec. Yeah, they made good things. Anyway, plugging that in the right way. Lights are still on, so no mistake. So here the blue line, I'm just measuring mains AC. 100 volts per division. You don't see the division raster, but it's a 300 odd volts that we have, or 600 odd volts peak to peak, which we have with our 230 volt mains. And the yellow line is connected. Oh, can I have that? Yeah, to the positive of the capacitor. And now look what happens if I click the switch without touching anything critical. And the division here is, what do I have here for division? 20 volts. So now it's at about 20 volts. You see it's discharging, so it's out of phase, of course. But as I said, now it's about 40 volts. The whole thing is, yeah, sizzling hot, so we have to wait a second. Because I wanted to see what the voltage set does. I think we saw it just for a second there. When I be a stupid user and just to keep the momentary switch, yeah, keep it pushed. We have mains AC again, and if I press the button and hold it press, the curve goes down to up to yeah, that's almost 60 volts. So yeah, and if I release it, it goes down to 40 volts. So yeah, it's inside the limit, but yeah, and yeah, the 130 degree switch kicked in again. So, bye.